Thank you very much. So I'm here to tell you one weird trick about macros in Racket and Scheme. All right, and so as mostly just a running example, I'll use continuation passing style translation because hopefully this is something you're at least somewhat familiar with, so you don't have to worry too much about why we're transforming or what we're transforming, but essentially how the transformation works. And so here is the kind of base, just continuation passing style translation. Very, very classic one. If you've seen it before, you've probably seen this one. If you haven't, you don't really have to understand what that code does. We're just trying to turn the left-hand side into the right-hand side, right? And so a great thing about Scheme and Racket and other languages with similar macro systems is that this is not just a theoretical tool, but actually executable program, right? So here is that exact same transformation written as actual code that, most of this I actually tested in Racket, but it's just as well in Scheme. It is the CPS transformation, and there's 3 steps, and the first one is what happens when you see a lambda. So the actual lambda symbol, let me see and make sure I'm in front of the mic. Yes, the lambda symbol is going to be kind of a special identifier we look out for, right? That's the first thing in the parentheses of the syntax rules. And so we say, okay, if I CPS a lambda, I see there's a parameter and a body, so then we rewrite it according to that specification we had from before. We're going to take a continuation and then return a lambda, or we're going to apply that continuation to a lambda with a transform body. If I see a single function applied to a single argument, we transform it. And in the last case, I hope it's an identifier because nothing here actually checks for it, but we're just going to assume that it is. And then we take the continuation, pass the identifier to the continuation. So this is fine, this works, and then you can write code and use it, right? So we can say define some example program and say it's going to be the CPS of this code, and it will do the CPS for us. So we can like play around with it for real, and then you can pass in an initial continuation and some parameters for f and x and get it to work, and you'll get the right results. But then if you actually peek under the covers at the expansion, it's not a pretty sight. And why not? What's the big problem is there's these reductions everywhere. So I've got a lambda k blah, blah, blah applied to a lambda f1 blah, blah, blah. And that's like a step that I should have gotten rid of, right? It's kind of in the way. It's not really relevant to the original program. It's this extra step. It's an administrative step. And ideally, we can get rid of that. And in fact, there are tricks to get rid of that. But what's the problem? Okay, so maybe this is slower, right? If our Scheme implementation is not smart enough, it may not get rid of these extra steps, so that might take extra time at runtime, and this is going to depend on your host implementation, how slow or fast this is. But that's not really my motivation, at least when I started thinking about this. It's just the fact that the output of macro expansion becomes very quickly completely impossible to read. And this matters a lot when you start writing your own macros that are doing these kinds of transformations. And if they're very higher order, it's hard to interact with them at the REPL because pretty much everything you see is either procedure or error, which is not very useful feedback if things are getting transformed into weird ways. And then the last resort is you open the macro expander and you say, what does it go into? And it turns into a mess. And then I have no idea what's going on. So just as a way to keep my own sanity while working on macros, I needed to have a more clean output just to see and tell what's going on. So, okay, what can we do about this? So there's actually a lot of literature about this on CPS in particular. That's why I used it as a running example, because this is a very well-studied problem. There are different techniques to get rid of administrative reductions sort of in advance to running the program. Here I'm focusing in particular on the ones that try to avoid creating the administrative reductions while the expansion happens, so like we won't output them in the code in the first place. And so here is a variant on CPS which does not produce the same administrative reductions. And why not? So we could actually get a regex in our output program, but that's because the programmer may have given us a regex. So if they say lambda x applied to something, then we're going to have a lambda x applied to something. But that's the programmer's fault. That's not our fault. So we can blame them. And then what's the other possible thing that might happen? So here, right, the way we've modified this CPS is that when we're translating both computations which take the continuation, and then we're going to put the continuation to where it needs to go. Right? So this is a form of doing this. I think the earliest one was from Plotkin. He had a colon translation was the name because he used a colon in the way that he wrote it. But it was saying, you know, if we translate a computation, you need to give me the continuation. I'll put it in the right place. And in these cases for application, we sort of create a continuation that is a lambda, which might get applied to a value, but that doesn't actually happen because the only time we supply a lambda continuation to this translation is if the term we're translating is not a value. So we never get this interaction between this lambda getting applied to a value. And again, the nice thing about Scheme and Racket is we can actually test this out. So you can take this translation. It's definitely more complicated. There's a lot more lines to it. But you don't have to worry too much about how it works. You can just dutifully translate this into some more macros, and that takes some more time. So don't worry too much about the details. But you know, if you're interested, you can look at the paper. But then actually test it out. So if we have this more refined translation that tries to avoid the administrative reductions while expansion happens, and we ask for the output, this is much, much cleaner. It's pretty much about the most direct form you could get, right? This is a normal form. Without supplying something for kf or x, there's no more reductions that could happen. So we really can't do any better. This is the optimal output. And so at this point, it's just you have to know a little bit about how CPS works. So I mean, I'm not saying it's great, but you're not going to do any better than this. So this is kind of the idea. So what's the problem here? So this is fine for these kinds of small examples, but it's not really, it doesn't scale very well, right? So this is a very monolithic approach. And if you want to add more language features, even the translation itself kind of blows up in size, right? Even this small little language which had only 3 things, variables, lambdas, and applications, what was a 3 different case translation became, I don't know, half a dozen, if not more. It's a lot more details to go through. And that's not super great, right? So really, ideally, if we're kind of doing this sort of stuff, a more modular style is better for your own reuse, for the users, and things like that. So how can we do something a little bit more modular is to, well, think about this, right? So especially in other languages like Haskell, what's very popular, the continuation monad. So you can think about the monadic interface, which breaks down what CPS does into these smaller primitive operations, and then you stitch those together, right? So what is the result of translating a term is going to be some function that takes the continuation, calculates the answer. And then the main ways that we use these is after I run a computation, we'll follow up by a continuation. And that's really just function application, right? And the continuation itself, if I want to use the continuation, we'll resume it with some number of values as arguments. And then again, that's function application. And then we also have the actual ways to kind of build these from small parts, which are return and bind traditionally. And this is kind of like the base thing. And then if you want to run a CPS term itself, then after it's done, we pass in the identity function, which just returns the final result that it calculated. And so you might think a little bit, I'll just kind of head off the question, you might like, why bother with after and resume? They are just function application. This is a very important tool we will use later. So keep that in mind. I know that it's trivial now, and they will not be in a little bit. So if you're wondering, that is important. But I think it's this kind of, we have a concrete set of operations for both introducing, right, return and bind, make new continuation passing style terms or computations, and after and resume, use them. Okay. So the advantage here is it's a lot easier to extend this kind of style with more stuff, with more language features, right? We don't have to have this one giant monolithic macro that takes a big grammar and then crunches it all down. We just have these parts that we can stitch together. And then you could extend it with lots of things, do notation and multiple argument functions and blah, 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 blah. Okay, so what's an example? So do notation is really nice for being able to actually use these and stitch them together. Wouldn't that be nice to have? So here's kind of an example of how these small little things work together. So here I wrote a macro called chain, and it's really just right association. So if you give me a sequence of operations, right? We can just nest them to the right. So if so each of these operations are going to take a number of arguments, and they're missing the last one because they apply to the thing on the right. And then here we've got the kind of do style, like let value. This is the left arrow of Haskell's do notation, which means run the computation and get the result. And that's just a bind, right? We just bind the name to so it's like, OK, this is a more comfortable way to write the same thing. It's a very short rule. And then you can do do notation, right? We can just chain a bunch of things together. So we can, if, what is H here? I think, oh no, H is the name. So we're taking some computation and then actually running it. And then we, with using let val. And then here there's a normal scheme let. Nothing unusual here, that we make a name, and then we do some more steps, and finally we return y. Right, so we can do this with a little sequence. So this is kind of the idea of why it's interesting. And we can still, write the original CPS transformation using these primitives. So we're doing a little bit less by hand, right? So same kind of idea, but it's a little bit more general now, right? So here I've got, instead of lambda taking always one argument, it's all of the param forms that Scheme supports, right? So any number of arguments, or maybe there's a rest parameter, or maybe you just take them all, right? So however that works. And then also if you apply a function to as many arguments as you want, there's another separate macro call which just unfolds all of that thing. And then here I've added return as sort of special keyword in case you just want to say run this expression outside of the CPS and return the value within. Okay, and then there's some extra helpers. Like for example, ret lambda means just return the lambda, things like that. Okay, so that's all nice and it's all modular, but then what happens again? When we expand the code, it's maybe even worse, which is not nice. So there seems to be this tension between compositionality, modularity, versus having concise, nice output, doing these optimizations and stuff like that. So can we have our cake and eat it too? So this is really about like trying to establish the modularity, compositional stuff, and then breaking that when we want to do these kinds of optimizations in the macro process. And so what's kind of the problem? So here, for example, it's a very small example. If I say, well, I want to return a value, and then after that, I want to pass the result to the continuation, really, I just want to apply the continuation to the value. But as I wrote it, these kind of expand on their own, and I get this kind of messy code, which has the extra intermediate step that I don't want. And really, what I would want to say is just fast forward that and just say immediately apply the continuation to the value. Right? But how do we get after to look ahead and sort of anticipate this next step, that after I am done with the return, in particular, not just in general, we want to kind of specialize that. And so the first kind of step is to say, well, here's a pair of, I make a new CPS computation using return, and then I immediately use it with an after. And then let's define the special case for what that means of that combination of use and introduction all at once. And so define what that shortcut should be, right? So we can say what that is. So this is just saying, well, after I return a value, and I need to continue with k, then that's the same thing as resuming k with this value. That's like a special case. If I see these two right next to each other, I want to do that. And then the general case, we can just generate by eta expansion. So you don't really have to write it twice. We kind of do, but the general case is always just going to say, here's the eta expanded form. So if I don't have the k at the moment, then just be a lambda that takes the k, and then do the general, or do the specialized case. And you do the same thing with bind, right? After bind is saying, well, I need to run m, bind the result to f, and then after that, pass the result of that to k. And if we're doing all of that, right, if I know that what the continuation is at the time that we are expanding the macro and creating the syntax, then we get these things. And there's two cases. So here, just look at the second case first, which is the more general case. I wish I could write it first, but we have to do the fall through at the end. So saying after we bind to continue with the k after, we say, well, the first thing we have to do is do m. And then after that, we bind the result to x and pass the x to f. And then when that's done, after that, we do the k. And because we have at compile time or at expansion time, we know what that k is, we can just stitch it in. We don't have to bind it to a lambda here. And this is sort of foreshadowing what the trick is, and it's maybe a little gross, is that we've got this lambda that we're looking at, and we're looking ahead and saying, well, if I'm binding to a lambda, I don't even need to do the application. I could just make it a let directly. That's kind of what the trick is going to be, is that we're going to look ahead a little bit and do this. And then we can do the general form as well. So this is the pattern in general. You have a use of something and the introduction through some operation. We want a shortcut to an after form. And so how do we do this in general is that it's these pairs of intro and eliminations. And after and resume themselves can look ahead and pull that out and do the shortcut. And get now the optimized form. So you can do the compositional definition, we still get the fully optimized CPS form. Okay, but there's still slightly another problem. This then becomes what after looks like. Every special case we have of a rewrite shortcutting, there's a lot of them, and they all are essentially of this form. After I return a value, I turn into after return. After I bind a value, I do that. After a let value, I've got a special form for that. And if none of those apply, I just do the normal thing. Okay, that's very redundant and kind of closed off, so not ideal. But they have this predictable pattern, right? It's always after some operation with arguments, I turn into some other specialized macro. And so we can capture that logic in just a big rewrite table of whatever cases we want. And then this is the worst macro magic. Definitely don't try to understand it right now, but it's doing the general case of looking up in the lookup table to see if I have a rewrite, performing that, and if I can't do a special rewrite, we just do the normal thing. And the advantage of this is, well, it's easier to write as a macro writer as long as you've got the magic, but also the user can extend it with new rewrites. So as a quick conclusion to wrap up, these are like kind of small examples, but yesterday I talked about at Olivier Fest some co-pattern matching code. And so I use this as part of debugging that. And you can try to quantitatively talk about how much smaller the programs, but I can say the user experience was I could actually understand what the expanded macros meant. And I could actually debug them. So that's the real reason I wanted to do this and kind of tell other people how they can do that too. So this kind of eases that tension. You can have both modularity and nice, efficient things by breaking that barrier using these kinds of rewrites things. So all right, that's it. I think I'll leave it there and answer any questions you might have.
Any questions? I can pass the mic, if so. Okay. Oh, okay. Student volunteer will, actually.
Thank you. Thanks for a very clear talk. So you're attempting to make two things coexist. The fact that the CPS transform as in one pass is a big step process, and then you want to achieve it somehow with self-organizing local processes, and then you kind of bend over backwards to make all of that fit in a beautifully elegant way. So there is a global property of the source program, which is the expression in tail position?
Is the expression in tail position?
And if it is, and if you have the ability to detect that, then there is no need for but you have that information. It's a static property, okay? And then rather than having your local macros that is testing essentially am I in tail position or not, and if that's the case, then I don't need to put a lambda, and otherwise I do, and that would buy you much. Now that's again initial tension between you want to do something global by assembling a lot of local things and make them self-organized in some sense, but still you're losing kind of technically the property that is in tail position. You're not exploiting it, and if you could, then everything which is around what you do if it's in tail position and what's not, you get for free. Without testing locally, because it's a global property. So couldn't you have something like an inherited attribute that says, I'm in a tail context, because essentially that's what part of what you do is doing. Do you agree?
So I think there's a couple things there. So there's a slightly different way you can kind of organize this, right? Mm-hmm. So rather than do the testing, you can kind of say like, oh, if I already have it, I think that's what you mean by tail condition, or tail position, right? We don't have to do the rewrite, which you can do it that way, but there is something else that you do lose, I think, which is, let's go to this one maybe? Yeah, maybe here, is then you can kind of, this can change. So the after can get eliminated, but then also the resume can get eliminated, and these can go back and forth.
But
so
only if it's in tail position. If it's not in tail position, you want all of that. But if you can distinguish that a priori, do you not then avoid all the test, the local test?
Maybe. I'm also not sure if I can detect that in general during macro expansion.
The macro expansion, indeed, that's a challenge.
Yeah. So this is specifically about macro expansion. So if you're in a more theoretical setting, you can have a lot more tricks in your toolbox.
Yeah, sure.
Yeah.
The challenge is that you want a bunch of local rewrite rules to self-organize to obtain a global property.
And it's just kind of thinking of it as like, when you're doing that, you can either change your translation or you can do rewrites usually after. This is kind of mixing those rewrites into the translation time without really changing the translation in the same sense. Yeah.
Now, distinguishing whether, like for applications who have value, computation, value, computation, that was also done in Sabre and License, very initial CPS transform.
Yeah, a bunch of people have done that. Yeah, I didn't cite it here, but yeah.
And that's losing compositionality. So it's a trade-off at every step. That's what makes it fascinating.
It's definitely trade-offs, yeah.
Question over here. Thank you.
If during macro expansion you had access to see the context in which you are expanding, would that allow you to eliminate these administrative reductions in a more simple way?
It might be, right? So it's almost like the return wants to know that if I'm in this context, then I could do that. And instead we have to wait until the context is there. So that might help. Yeah, I think so. Yeah, and that's kind of why we had to introduce this sort of what was a trivial macro, because that's what's actually going to do all the logic. And this is kind of like we wouldn't need that if we could just detect if we were in tail position, which is not normally something you have in macro expansion. So we're kind of inventing that information, and it's a little bit roundabout, but that might be another way to do it if you had that
So we need macro expansion with context.
Yeah, that might help. I don't know exactly how that'd look like, but that might make it a little bit simpler, yeah.
I have a few ideas.
Yeah.
I forgot to ask, what about conditional expressions when you intention to duplicate the context?
So for those, so that is something that came up in the real use case for co-patterns, and all the ones I showed, you don't duplicate it, and reasonably you should be very careful not to duplicate serious code. And so basically for that, there's like kind of I had separate ones saying like, I'm willing to inline this, which is usually because it's just an identifier. And if the user gives me something, so the ones that the users really use, whatever they give me, I'm assuming is very large. And so that initially gets bound to one variable, but then that gets copied wherever because it's just a single identifier. Maybe, yeah.
It's okay to duplicate the continuation because it's just okay. If you're not in tail position, danger will always.
I don't know, but duplicating inflates the code size then, so that's another challenge.
And it doesn't matter if you're in tail position because the continuation is just an identifier.
Oh, I see what you're saying. Yes, if it's just an identifier, then that's fine, yeah.
So again, an a priori, it's all about inherited properties versus synthesized properties. Yes. And you're trying to build everything on synthesizing properties and then trying to manage, and that's the essence of the fight. If you were to do both, inherit some, synthesize some, then you would be in a much sweeter spot. Where I believe but on the other hand, you're doing it with macros. So.
Yeah, doing it with macros. Yes, if I didn't have to do it with macros, there's so many easier ways. This is just how to get it to work with macros. That's the point of the talk.
Okay, let's have Sean start setting up.